So welcome. So continuing this this part E for us, which is it's a long section. We're building a lot of skills. We're going to go to the next level and say, well, okay, I understand that I can look at things in two orthogonal axes, and as long as I keep all the x components with the x stuff and all the y components with the y stuff, I can find the x component of the answer and the y component of the answer. And often that's enough, but if I need to, I can use Pythagoras and bring it all back together to get the final answer, you know. So I do all the x, I do all the y, I get the x of the answer, I get the y of the answer, I bring it all back together and I get, oh, it's over there and it's going that fast in that direction and so on. I can do all that. But, you know, we just spent a bit of time learning IJK notation, which is basically a shorthand way of codifying components in the three axes, not the two, but the three. So surely I can do IJK with this. And it turns out in many cases I can. Not all. And so this tends to be taught as a interesting bit rather than this is what you really got to learn. I mean, I better state that more clearly. You really got to know components. You got to know doing the x component and the y component, and you got to be able to do those. Because that's kind of bread and butter. But under some circumstances, we can use an IJK as a shortcut method. And I want to show you that. Both types of questions are legitimate, but this is kind of like, it works in a fewer set of equations. It's quicker, but it works in a fewer set of occasions. And the idea is, it's kind of like, let's see if we can do this with vectors. So rather than having VF equals VI plus AT, let's say vector VF equals vector VI plus vector A. T, of course, is not a vector, so it's just times T. That's just basically an equation with three vectors in it. We can add vectors, that's no big deal. We don't call it delta X for displacement. Traditionally, the book calls it delta R because it's a vector. Okay, don't know which direction it's supposed to be in because all vectors have different directions. So we say vector delta R, the displacement of my vector, my answer, is equal to a half VI plus VF times T. Displacement of my vector is equal to VIT plus 1/2 A times T squared. And VF squared equals VI squared plus 2A delta, not delta X, but delta R. If you write them down with delta X's, no one's going to care. It's not like they're going to go and say, oh, we got the equation wrong. It's just, it's like, do you call it a hat or a cap? Delta R and delta X are about the same thing. Interesting thing, though, is, you know, you've got some squaring going on with vectors. And I don't remember doing that, so I know how to add vectors, I know how to subtract vectors, I know how to multiply vectors by a scalar. And in a bit, I'm going to learn how to multiply a vector by a vector. In two different ways, actually. But, you know, I'm not there yet, so I'm gonna hold off on that. So I can't do all the equations with it. The two most common ones that I can do are just these two. I can turn around and say, well, now let's think about this from math point of view. Vector VF equals vector VI plus vector A times the time interval. But these are vectors. So we should be able to draw these things and do a vector diagram, which works. Let's only play with 2 dimensions so that we can see it. In 2 dimensions, my vector VI might look like this brown line. And A times delta T, I put down A times T, it should be delta T. A times delta T is the green line. And the process of adding them together is you put the tail of one of them on the head of the other one. So by just drawing that brown axis, brown arrow, then drawing the green arrow, I have added those 2 vectors together. And my answer begins at the beginning and it ends at the end. And so that blue line is my answer. So this is it abstractly in an equation form, and this is it graphically. And that's what we began with. We began by adding vectors like that. So okay, I can do these things graphically. I can visualize them graphically. It's not just abstract math. The abstract math describes an image, which is an abstract image. It's just different ways of looking at the same thing. If I want to look at this one, now I have, this is basically delta r, so this is a displacement vector, is equal to vi delta t. Again, I put down, I did these diagrams before I started going to delta t, plus a half delta t squared. And again, you add these two guys together, so there's the process of addition. So again, I can visualize these things. I can write it down as an equation, which I already know, because I learned these equations. By the way, you've got to know these equations for next time for sure, I think. And then particle has an initial velocity of 3 minus 2j plus 4k. It has an acceleration of that. What is its vector velocity after 6 seconds? So again, I'm always keen. You've got to visualize. You've got to visualize, visualize, visualize. So particle's initial velocity, let's start off at this point here. And there's my initial velocity, there's my VI. And it has an acceleration. Acceleration. My acceleration is going to be down here. My acceleration. It's a constant acceleration, or else these equations don't work. So it's a constant acceleration. And I want to know what is the vector velocity after 6 seconds. So this thing's going to move around a bit. The actual path followed by this thing is going to kind of move around a bit like that. And it may be that at t equals 6 seconds I'm here, and it may be that my v final is there. All I can say for sure is that throughout this journey I have this constant acceleration. Isn't that right? It's a constant acceleration, or else I can't use these equations. And, you know, it kind of is going to have an effect, something like that. Okay. There's my visualization. You don't have to visualize in that detail, but the more you can visualize, the better you become. It's like, you know, you can get stronger and stronger and stronger by working at visualizing better and better and better. And then you turn around and say, well, okay, there's my diagram. I'm not going to say find VF final using X components or VF final using Y components. I'm going to say find vector VF using vectors. And then I say, well, what vectors do I have? I have VI is equal to, and I look on here, and there's my VI. So it's plus 3I minus 2J plus 4K. That's going to be in meters per second, of course. And then I have my constant acceleration. It's a vector. My constant acceleration is given by this guy, which is minus 2I plus 4J minus 6K. That's in meters per second squared. It says after 6 seconds, so my delta t equals 6 seconds. I suppose I could have said not a particle initially has a velocity. I suppose I could have said at t equals 3 seconds, the particle has a velocity of this. And what is the velocity at 9 seconds? And then you'd have to know not to use the 9, because I didn't tell you about the 0 seconds. I told you about the 3 seconds. So you've got to distinguish between t and delta t. Delta t is the time interval between the beginning and the end. Just happened in this case, I started you off when the clock was 0. So you've got to watch out for that. Again, we're trying to make sure that people are not just like, oh, every time I see a V, I put that number in. Every time I see an F, I put that number in. Oh, yeah, there's my answer. I have no idea what I just did. At USF, we got these computer labs years and years ago. I inherited them. We had 2 computer labs, and one of them was doing Ohm's law, which is basically measure current versus velocity, voltage. Why you'd want to use a computer lab for that, but we did it. And I was just really curious about this, because it's like using this huge machine just to do something that's really simple, and you know. And at the end of the lab one day, I sat aside and I said, "Did you just finish that lab?" And they'd say, "Yeah." And they kind of knew I was a teacher, but I wasn't their teacher, so it was like, you know, they were a bit like, you know, who are you? But, you know, they'd see me around. And I said, "So what was the lab about?" And they'd say, "Using a computer." And I'd say, "Really?" But wasn't there something about electricity? Oh, yeah, we connected this thing up so we could use a computer. So the lab, which was about V equals IR, became using a computer because it was this like huge machine to do something that's really simple. And I think there's always that fear that people will go into just autopilot. And the reason why you don't have lab books in my lab is because we complain that students do nothing but follow recipes. Then we give you a recipe book and say, get on with it, you know. So you've always got to put yourself in the teacher's mind. What's the teacher trying to do? And I'm trying to make sure that you're not getting by just by plugging numbers blindly into equations. So little things like that where I can just change the language. So you've got to visualize it. Stuff like that is going to come up. So don't be surprised when, oh, this time he didn't start us off at t equals 0. He started off with t equals 3. So do, in your preparation, get ready for that. So I know my delta t equals 6 seconds, and then what I want to find, Vf is equal to that. So then I come along, and you know, these equations are all the same, so it's going to be, Vf, vector, equals Vi, vector, plus A, delta t. And when I first started off, I didn't really care about these arrows. They were like a bit of a pain. And I found when I started caring more about the arrows, it became clearer to me what's a vector and what's not a vector. And things got a bit simpler for me. Now, I need a kind of like, I need a rubric for adding up vectors so that I don't get, you know, a mess. So basically, what I like to do is I put down a grid. I just think it's a nice, neat way of keeping track. You don't have to make it elaborate. You can just, you know, keep it relatively simple. And I look at my equation and I say, well, the first thing I want to do is have vector Vi. And I look at my list and I go, that's plus 3, minus 2, plus 4. And then I look over here and I say, well, I want A times T. So I'm going to go A delta T. And I'm going to look here, and it's only A6, and it's right next to it, so I can do that in my head. I can go minus 12, and I can go plus 24, and I can go minus 36. Just check I did that right. Yep, I did that right. And then the operator here is addition, so I put down add here, just so I know that I did the addition. Then I'm just adding up, and I go minus 9. I'm going to go plus 22, and I'm going to go minus 32. And then to write it out nicely, I go minus 9i plus 22j minus 32k. Put my little hats on, put my brackets on, remember my units, meters per second, put it in a box. And do you need to use that grid? Probably not, but I found when I started using that grid, the layout became much more manageable. I made fewer slips. So we just did a 3-dimensional projectile problem using basically the same equation and the same math skills we use. In fact, in some ways, it's easier than doing it using components. You know, it just fell out. It just fell out very nicely. So it's a really powerful technique. It does not work for every occasion, and that's why we don't just go to it. It doesn't work for every occasion, but it works for some of these equations really nicely. Questions on that? I can make it a bit more interesting by simply telling you it's a projectile. Now I've told you the acceleration. What is the acceleration vector for a projectile? Can you write that down for me? Because there is a direction here. So what is the acceleration vector? Commit to it. Just commit to it. See if you're right. If you commit to it and you find you're wrong, you know I need to study this a bit more. If you commit to it and you find you're right, you can check it off. If you don't commit to it, you have no idea whether you really knew it or not. So think about it. If I said, what is the magnitude of the acceleration vector, you'd say 10 meters per second squared. And you'd probably say 10 meters per second downwards. And because when you're working in the y-axis, downwards is negative, you're probably used to saying minus 10 meters per second squared. But that's in one axis. Now you've got 3 axes to deal with. And if you're using standard axes, x bin horizontal, y bin vertical, z bin towards you, then basically you have no I, but you do have minus 10j, and you do have 0k. So it's a three-dimensional representation of the same thing, but it's not just minus 10. It's kind of like it's a vector, so it's got to have a thing. I don't have to tell you that. It's kind of like it's part of the. As soon as I say projectile, that's set. So I can say, well, delta x equals vi delta t plus a half a delta t squared. This is what's going on basically. When we talk about free fall, actually, we're falling away from the path that we would normally have. And because of that acceleration, that half, I call it g here because sometimes the book calls it g, but I really prefer a half a delta t like the equation says. But when we have that, that acceleration multiplied by the time, what we have is this basically this fall away in a very specific direction. So even though this is climbing in the air, it is falling below where it should be, and so we call it free fall. Even though you're going upwards, it's still free fall because you're falling below where you would be if there was no gravity. So that's the kind of logic behind that. And we have an example here. A projectile has a initial velocity of that, and what is its vector displacement after 3 seconds? Very little said on this one. So again, it's important to visualize. I'm not going to make any attempt to draw this to scale. It's a vector. There's my initial velocity. So this is my vi. And it's a projectile. So I know that I have an A. Can you see how a different coloured pen would be really nice here? I can't just click on my pen to change the colour. It's a bit annoying really, but can you see? I'm going to show you something now. If you just do that, can you see how you're much less likely to confuse those two vectors because they're in different colours from each other? It just distinguishes them in your mind. So especially when you're first beginning. I love those 4-click pens that you can find at, the stores sometimes. I used to have 4 different colours, and then I got rid of those, and now I don't have anything. I use this thing. And my one disappointment is I wish I could have 4 colours at the top, so I could just keep going backwards and forwards between the different colours, because it does make a difference. But anyway, so, and then, let's go to another colour. Oops, that didn't work. Yeah, this is going to be. So then what happens is, of course, this thing, and again, it's going to go, tries to go in its direction, but it's modified by its acceleration. And then it says, what is this displacement? So now we have a displacement. So there's my delta R. And this is at t equals 0. This is t equals, let's call it delta t seconds, whatever it is. So there's my visualization. And I want to codify it, so I'm going to say, well, my VI is equal to plus 5I minus 4J plus 6K. That's going to be meters per second. And then I'm going to say my acceleration vector is equal to 0I minus 10J plus 0K meters per second squared. And again, that's just conceptual understanding. And my delta t after 3 seconds means that delta t is the after 3 seconds, means delta t equals 3 seconds. And I want to find my delta x, or delta r. Makes no difference. So I say, okay, well, delta r equals vi delta t plus 1/2 a delta t squared, and make it vector form. I put these little arrowheads over all the vectors. And then I need a grid system, so I put down my ijk in a little box. Just to keep it nice and neat. And then over on the side, I like to write down what I'm doing, because I am going to check this at the end of my test or whatever. So I do want to know what I did, where I did it. I'm looking at put this situation up here, and this is my VI, but this is my delta t, and I've got to multiply those guys together. And I feel comfortable just saying that's going to be 15, and that's going to be 3 times minus 4 is minus 12. And that would be 3 times 6 is plus 18. And I think I did that right. 5 minus 4 and 6. 5 minus 4 and 6. Yep. And then I have a half times A times delta t squared. So now I've got to be a bit more careful, but it's multiplying by 10, which is okay. V squared is 9, and a half of 9 is 4.5. So 4.5 times 0 is 0. 4.5 times 10 is minus 45. 4.5 times 0 is 0. There's no shame in doing that as a little aside calculation, you know. But it's relatively straightforward. I feel comfortable I can do that in my head. So I add these two guys up because the operator says to add, so I add. I'm going to go plus 15 minus 57, I think, and then plus 18. So my answer is plus 15i minus 57j plus 18k. Put it in parentheses, give it some units, it's meters, put it in a box. And there's my answer. So for sure, you're going to get some kind of projectile being fired, and the expectation will be that you will do it using x-axis, y-axis components. That's going to be on there, because that's a skill that you just need. You're going to need that skill for when you're doing resolution of forces, when you're doing Newton's laws. That skill, dividing things into x and y planes, is just, very important. You're quite likely to get something with this as well, because IJKs are really important. We keep using them all the way through physics 2. So every chance I get to test you, can you practice this, is important. So I expect something along these lines as well to be in there. So we've done motion in 2 dimensions. We've done it as like a tabletop motion where you don't know what the A is vertically in X and you don't know what the A is in Y, and that's just the way it is, like a machine tool. Then we did projectiles where you know what the acceleration is vertically because it's the acceleration due to gravity. We did that using components. And then lastly, we've done it using IJKs for 3-dimensional stuff. As I say, when I was a student, I struggled with components because I didn't do the right diagram. And then I finally sorted that out, and you get really good when you struggle with something and you solve the problem. You've done all this practice, and it's this problem over here. So you practiced all this stuff over there, you sort that problem out, you're really good at the whole thing. So I was like really good at components then. And then these guys came along, and all the examples they gave us were 2-dimensionals, and I can do, I don't need this. Who needs IJK? I can do this. So I did not practice my IJKs. And later on, I get a problem which is in 3 dimensions, and I'm writing all over a page trying to solve this thing, and it's a nightmare. And all I had to do was IJK, but because I didn't see the value in it, I didn't practice it, and so it was a hole in my armor. So everything's introduced makes you more powerful. So my attitude was I wanted to survive the course as undergraduates. I just wanted to get through. I want to be okay. And when you set that as your bar level, when you think that's as good as you can do, that's what you kind of steer yourself towards. And it never really occurred to me that I was very fearful of wasting time. I was very fearful of learning the wrong stuff. So I put myself in this impossible situation where I'm trying to glean from the instructor what the instructor wants so that I know only what they want. Because that's all I'm going to be tested on. But I had no idea what the instructor wanted. And in retrospect, if I had just been more willing just to practice, and build my skills, if I'd saw it more like me just getting stronger in myself, it just feeds itself. This bit over here, maybe you won't be asked a question on that bit over there, but that skill is going to be over there, and you're going to need it for a question. So practice on these things. This next thing is a little bit of an aside. It is 2-dimensional. It does use IJK notation. You might have come across some questions like this. I seem to recall on some aptitude test I had where it was, Johnny gets on the school bus and runs towards the back of the school bus at, 5 meters per second, while the school bus drives forward at 6 meters per second. What is Johnny's speed relative to Johnny's mom and all that kind of stuff? It's like you're trying to draw these things, well, one's going that way, one's going that way. And it's easy to get them backwards, Can you imagine doing that in 3 dimensions? Johnny sails his boat in that direction while his mum takes a balloon up there in that direction. And what is, in the meantime, Sam is swimming in this swimming pool. What is Johnny's velocity relative to Sam swimming in the swimming pool? It's like, it's a piece of cake with IJK. Because, let's think about our vector diagrams. If this is vector A going to B, A with respect to B, it's really B with respect to A when I think about it, B with respect to A. If this is the vector linking A and B, and that is the vector linking B and C, then this is the vector linking A and C. That's addition, isn't it? That's addition. When we do vector diagrams, when we put the tail of the second one on the head of the first one, that's how we add. So that's addition. That's not addition. That's not addition. They're not, tail and head are not together. That's not addition. So on this vector diagram, that's addition. So we can say, this vector replaces that vector plus that vector, and not the other way around, no other combination. So, what we do is we say V, now let's think about it from an equation point of view. We start at A in both cases. We've got to start our answer at A, so it's the right answer. We've got to start our sum at A, so it's the right sum. We've got to end at C. We've got to end our answer at C. We've got to end our sum at C. What else do we have? We have B. So we go A, B, and then BC. It can't be any other combination. If I said AB and then CB, it would be that. And now, these are not adding, but those are. So let's do an example and I'll show you how it goes. John has a velocity of that relative to Bill. So there's velocity of John, and it doesn't matter the language, just keep the order the same. So-and-so relative to so-and-so. I'm not going to try and trick you with that. But so make sure you put on, John, Bill. So John relative to Bill is that. And Lisa has a velocity of that relative to Bill. So we can have, let's see a look. Lisa relative to Bill. So there's my V, Lisa, Bill. And then what is the velocity of Lisa relative to John? So I'm looking for that. So that's what I'm looking for. V, Lisa relative to John. So I went John, Bill, JB. I want Lisa, Bill, LB. And I want Lisa, John, L, John. The diagram doesn't matter so much. If you mess up on the diagram, you can still actually get the answer right, because you're going to just solve it using your equation. But what you're going to say is, you're going to say the velocity of John relative to Bill is equal to the velocity of John relative to somebody else plus the velocity of somebody else relative to Bill, because we start with John and we end with Bill. And, oh yeah, it's Lisa that's in between. So there's my equation. I know my equation is right because I started with John in both cases, I ended with Bill in both cases, and Lisa was the intermediary between the two. And if I look down at my diagram, does that make sense as well? So I'm going to say Lisa, John, plus, well, I'm not sure I got my diagram right. Let me just stop for a minute and just think. So this is John relative to Bill. And, oh yes. So that's John. So let me sort this out. So this is saying that velocity of John, Lisa to Jill plus the velocity of John to Bill is equal to the velocity of Lisa to Bill. So that's what I have done in my diagram. Now, I want that guy. That's what I want. So let's rearrange this. So I say John Bill is equal to V Lisa Bill minus, take that to the other side, becomes minus the velocity of Lisa John. And then let's rearrange that so that I can get rid of that negative sign. Well, that's the velocity of Lisa to the Bill plus the velocity. And the way I get that minus to become a positive is I change the order of these two. Can you see how that guy there is that guy there, and that guy there is that guy there? So the equation and my diagram were the same. It's just, you know, they've written in different forms. Yeah? To get the answer right, you don't need to have the diagram right. It's nice if you do. You do have to have the equation right. So you've got to, if need be, just learn. I'd like you to understand why. But if need be, just learn that you start with the first letter, you end with the last letter, and you put the intermediary thing in between. So then I turn around and I do it. So I'm going to, I go I, J, K. And the first thing I have is velocity of John relative to Lisa. John relative to Lisa. I have Lisa relative to John. I'm sorry. John. I'm sorry. John relative to Lisa. I have Lisa relative to Bill. And John relative to Bill. Oh, I'm sorry. Duh. I'm sorry. I read the wrong bit. Let's get rid of all that because I answered the wrong thing. Let's go here. So, it says, what is the velocity of Lisa relative to John? So, velocity of Lisa relative to John is equal to the velocity of Lisa relative to something, and the velocity of something relative to John. So that's going to be Lisa relative to Bill, and Bill relative to John. So there's my classic equation. I start with Lisa, I end with John, and I put Bill in between. Yeah. So now down here, I want velocity of Lisa relative to Bill, and I look here, and I have Lisa relative to Bill. I'm given that. V Lisa relative to Bill is this guy. Minus 2I minus 3J plus 4K. Notice I did not put my list down, and I'm paying a price for it. So shame on me for not writing my list down. But nevertheless, the velocity of Lisa relative to Bill is that. So it's minus 2 minus 3 plus 4. Then the next thing I want is my velocity of Bill relative to John. My velocity of Bill relative to John. And my velocity of Bill relative to John is not given. I have John relative to Bill. So it's minus the velocity of John relative to Bill, because we're in opposite directions. Okay? So this is going to be minus, and my velocity of John relative to Bill is going to be 3I plus 2J plus 4K. Oh, so my velocity of Bill relative to John is minus 3, minus 2, and minus 4. It's the opposite of this guy, if that's in the wrong direction. So then I just say, well, that tells me to add, so just add. and I go minus 2 plus minus 3 is minus 5, minus 3 plus minus 2 is minus 5, and that's 0. So it would be minus 5i minus 5j plus 0k. I am looking for, this is a velocity of Lisa relative to John. It's a velocity, so that would be meters per second. And there's my answer. So I think I met heavy weather with that because I was, because I read the wrong thing to answer, and also with my, well, that's why I had to mess with my diagram actually when you think about it. And I didn't put down my list, which is a shame on me, not putting down my list. But basically, it's just, you've got to know that equation. The velocity of the clock relative to the flag, and I have the velocity of the flag relative to the computer. What's the velocity of the computer relative to the clock? It's going to be the velocity of the computer relative to something else, the flag, plus something else, the flag relative to the clock. You just begin with the beginning and you end with the end, and you put your other thing in between, and you get the right answer. So what might, at first, if you're trying to do this in your head, would be like confusing and complicated, becomes really quite straightforward. Okay. Cool. Let's